Hello everyone. So next we'll see the pipelining. So this is one technique to achieve parallel processing. So this is a technique of decomposing a sequential process into sub operation, with each sub process being executed in a special dedicated segment that operates concurrently with all other segments, so you can overlap, right? So as an example, let me give you the example of industry assembly line. So the car that you want to build, right? So first some person take the structure of the car, then in the next segment they fix the engine in that, the next segment they fix the tires, then glasses in your car, and at the end they color the car. So this way they decompose the construction of whole car into different segments. So when one car is moved to the next state, the next car construction can be started, right? So this is the example of pipeline. Let's see the example, right? So suppose I want to perform this operation ai into bi plus ci and I from 1 to 7. This operation I want to perform. So how I can do it? So this task can be divided into sub operation in each segment of pipeline. Like, first get the value of AI and BI into register, that is R1 and R2, right? Then after that multiply those registers, right? So we are performing this multiplexes. At the same time you can load this C into register R4, right? And at the end now we have this multiplication and this C, so then we can perform the addition, right? And the result that will store into R5, right? So if I draw it, so it will be like this. So first in register we will load in both the register, right? R1 and R2, right? We will load it. Then we will perform the multiplication. So this is for multiplication operation. So we'll feed this R1 and R2 into multiplication and we'll get the result. At the same time in R3 what we'll do, we will load C, right? This is B and this is A, right? Then we have performed this. After that we will add this. So this is the addition. So this result and this result will fed to addition operation, and then the result will be in R5, right? So you can see this is the one segment, this is the second segment, and this is the third segment, right? So now let's understand with the help of registers this pipeline example. So at each and every clock pulse they move to the next segment, right? So we have three segments as I have shown the previously: segment 1, segment 2, and segment 3. 5 register we are using: R1, R2 to load A and B, R3 to store the result of this multiplication, R1 multiplied by R2, right? And R4 to load C, and at the end R5 to store the sum of R3 and R4, right? So at the first clock pulse what happened? The value of A1 and B1 that will be stored into R1 and R2, right? Then in segment 2 and segment 3 there will be no activity right now, right? At the second clock pulse, right? So when you give second clock pulse, at that time you have loaded the value of a1 and b1 into r1 and r2. So next phase, segment 2, what it will perform, it will perform this multiplication of r1 and r2, means a1 and b1, and at the same time it will load the value of c1 into r4, right? So a1 into b1 means this two register multiplication it will perform, and then c1 that will be loaded into r4, right, at the second clock pulse. Now you see we are in the second segment. Now first segment is empty, so you can start the next task here, that is to load a2 and b2 in r1 and r2, which is required next. So you can load a2 and b2 into r1 and r2. So you can see at the clock pulse 2 we have overlapped these two things, right, second segment and the first segment. So this way you can achieve the parallelism. Otherwise what will happen, first you will do this a1 b1 without pipeline, right, then next a1 into b1 and c1 you will load, and at the third you r3 plus r4, that is a1 multiplied by b1 plus c1. After that you will start next, that is load a2 b2 into r1 r2, then perform multiplication, that is a2 into b2, and load c2 into r4, and then perform the addition. This will go in sequential, but now you can see the first clock a1 b1 that is loaded into r1 and r2. The second clock pulse, this multiplication will be taken place a1 into b1, and the c1 will be loaded into r4, right, and at the same time, at the same clock pulse, this a2 and b2 will be loaded into r1 and r2, right. Now in the third clock pulse, the a1 into b1, right, plus your c1 means r3 plus r4, so it will perform the first operation, that is ai into bi plus ci. Now I is 1, so first operation is performed here, okay. So at the third clock pulse you will get the first result, that is a1 into b1 plus c1, and we want to go up to 7, from 1 to 7. So at the same time in segment 2 what will happen, a2 multiplied by b2, a2 b2 is now loaded, so it will perform this a2 b2 multiplication, and the c2 will be loaded into r4, right, and here it will load a3 and b3, right. Now in the fourth clock pulse, now you will see this will go here, this will go here, and next is a4 b4. So in the fourth clock pulse what you will get, you will get the result of a2 multiplied by b2 plus plus c2, right, this result you will get a2 multiplied by b2 plus c2, okay. So now you see, to get the first result we wait for 2 cycle, and in third cycle we get this result a1 into b1 plus c1. To get this result only one cycle, means in next cycle we are getting this result. Same way in fifth cycle you will get the result a3 into b3 plus c3. So now at every clock pulse you will get the result, right. So here now you see a6 into b6 plus c6, c7 will be loaded into r4, a7 multiplied by b7, right, and that is loaded in clock pulse 7. So in the 8th clock pulse there is no operation in segment 1. Same way at the 9th clock pulse, the segment 3, there will be operation in segment 3, and a7 into b7 plus c7, and there will be no operation in segment 2 and segment 1. So you see there is some pipeline in this, right, each and every operation that is going through some pipeline. So if I see give you this example pipeline, and segment 1, segment 2, right, so this is segment 1, this is segment 2, and this is segment 3, right. So segment 1, load R1 and R2. So first it will go, so first it will load R1 and R2, first instruction. Now first instruction will go here. At that time second instruction will be here, right? Then next clock pulse, first instruction here, second here, and third will be here. So this way it will go, and you can see once after third clock pulse you will get the result. Then after each cycle you will get the result like this. So to get this first result we will waited for 3 cycles. After that each cycle we are getting the result, right? So you can see we have achieved the parallelism. This is not the case. So first one instruction is over, then you will go for second instruction, then you will go for third instruction, right? So in that the second another segment will be waited. So this is the diagram of 4-segment pipeline, right? So in this segment 1, segment 2, segment 3, segment 4, and they assume that they have a same time, right, to execute some operation. Now to pass this value we have intermediate registers. They are working on the same clock pulse, right? So it will store the intermediate result between two segments. Now this is a space time diagram, right? So in the space diagram this horizontal thing, that is the clock cycle, right? So it will indicate you where your task is or how that task go through, and this indicates your segment. So this is a 4-segment task, right? And we have a 6 tasks to complete, and each task will pass through 4 segments, right? So in the first clock pulse, T1, right? So task T1, that is in first segment. Now at the second clock pulse, when task T1 is in second segment, the task T2 can be placed in segment 1, right? This now in the next clock, the T1 is in third segment, T2 is in second segment, and T3, that is in first segment. In the fourth clock pulse, first you will get the output, that is of T1, right? Your task T1 is over at the fourth clock, right? T2 is in third segment, T3 is in second segment, and T4 is in first segment. Now after that, once task T1 is over, after that at each clock pulse you will get the result, right? And at the 9th clock pulse your task, right, all the 6 tasks are over. Okay, so task is a total operation performed going through all the segments in the pipeline. So all the segments 1 2 3 4, that is your task, right? So T1, that is your task. So we have performed that task after going through all the segments, segment 1 2 3 and 4. Now how to measure the performance of this? So we can measure using Speedup. Now what is Speedup? So Speedup you can measure like this: time to complete n task with non-pipeline unit upon time to complete that n task with pipeline unit, right? So non-pipeline upon pipeline unit, if you divide it you will get the Speedup, and this way you can measure the performance of pipeline unit. So let's calculate it, and what is the equation of, let's derive it. So there is a k segment pipeline with clock cycle time Tp to complete n tasks, right? The clock cycle required to complete n tasks, right? Clock cycle time required to complete n tasks. So how many clock are required? So to complete the first task, we require the number of clock that is based on how many segment we have, right? And here we are considering one segment is equal to 1 clock, and this is time given for 1 clock, right? Here we are just measuring how many clocks are required, right? And if you multiply this with the clock time, we will get the time. So the for first task out of n tasks, the time required, that is k, because it need to pass through k segment to get the first result. After that, at each clock you will get the result, right? So how many tasks is now pending? So out of n, one task required k, so remaining n minus one task, right, require one clock cycle. So you can add plus n minus 1. So this many clocks are required to complete n task, right? Now to complete the n task, right, what we can write? So simply just multiply with the clock time, that is your clock cycle time. So you can multiply this k plus n minus 1 into tp. So this k into tp means time to get the result of first task plus time to get the result of remaining n minus 1 task, right? So simply you can write like this for pipeline unit, k plus n minus 1 into tp. For non-pipeline unit, right, if we don't use pipeline, then tn, that is to complete each task, time to complete each task. I am talking about task. So there are n tasks, so time to complete all the tasks, that is n into tn. Tn is time to complete one task, and how many tasks we have? We have n tasks, so that is n into tn. So now if we'll put this equation in this equation, so our speed up s is n into tn, that is non-pipeline unit upon pipeline unit, that is k plus n minus 1 into tp. This is the equation to achieve to find out the speed up for any pipeline approach, right? So you will get the performance evaluation of your pipeline approach compared to your non-pipeline approach. Okay, so this is the equation. So tn, that is task time to complete one task, tp is a clock cycle time. Okay. Now, as the number of tasks increases, that n becomes much larger than your k minus 1, and that k plus 1 n minus 1 approaches the value of n, right? So that k minus 1, that is negligible, you can neglect it. So in that condition, your speed up, that become tn upon tp. Tn upon tp. Tn is time to complete one task. TP is a clock cycle time. Now if we have Tn is equal to k into Tp, means this is the whole task, and each segment takes Tp clock cycle time, then you can write the speed up is equal to k into Tp upon Tp. So this will be cancelled out and your speed up, that is k. So this is the maximum speed up that is pipeline can provide, that is based on number of segment, right? But here we assume that each segment taking the same time, right? So this is the maximum speed up that pipeline can provide. Okay. Let's take the example. So you have total 100 tasks, clock cycle time is 20 nanosecond. How many segment you have? 4 segment, and time to complete each task, that is 80 nanoseconds. So you can see 20 multiplied by 4, that is 80, right? So speed up in this case, that is non-pipeline upon pipeline. So non-pipeline, that is n into tn, that is 80 upon 80 multiplied by 100, that is 8000, divided by k plus n minus 1 into tp. So that will give you 2060. So the speed up is 3.88. So this pipeline approach is 3.88 time faster, right, compared to your non-pipeline approach. So reason for not getting this maximum speed up, So we have achieved this speed up, but theoretically it is not uh, possible to achieve this speed up, right? Because the different segment may take a different time. Here we have assumed that each segment taking the same time, but practically different segment takes a different time. So some person is uh, making the structure of car, that takes different time. Some another is attaching the engine, that takes a different time, right? So it depends on that. Then another is, when you cannot go with the pipeline, you can have multiple function unit in parallel, that we have seen. So the same task you can have for different data, right? So same operation I am performing, but here I will get the different data. So this you can say it's a SIMD approach, single instruction multiple data. Okay, so this pipeline that is applicable in arithmetic pipeline, right, where you can divide the arithmetic operation in sub operation. The example we have seen, the whole arithmetic operation we have divided in sub operation. So arithmetic pipeline is possible. And the next is instruction pipeline, that is also possible. So in instruction pipeline, overlapping the phase of instruction. So in instruction, when I write some instruction, suppose add R1 R2, right? So at that time, add R1 R2. So first it will fetch the instruction, right? So from memory it will get this instruction, then decode the instruction, means it will get to know about what is the operation to be performed, where the operand is, the addressing mode of the operand, then the execute mode. So it will now perform the operation on the operand. So this different phase, or these different phases that can be overlapped in a pipeline mode, and you can achieve a parallelism, right? So we'll see this thing, arithmetic pipeline, instruction pipeline, in detail in next lectures. Thank you.